Then how do I take this to, yeah, okay, great.
All right, so thank you, Tushar, for that introduction. So I think, no research is done in a vacuum, or if you're doing research in a vacuum, you're kind of doing something wrong, right? So I want to acknowledge my collaborators, especially Professors Joel Emmer and Vivian Z at MIT. Most of the slides that I'll be presenting today were taken from their class that they just recently did in the fall, Hardware Architectures for Deep Learning. It also includes slides from my colleague Anshuman Parashar, who's also a senior research scientist at NVIDIA, and of course was influenced by several people at NVIDIA and several former interns who we've had as well. I want to also run this talk like a class, so please feel free to interrupt with questions at any point. Just raise your hand. If you have any clarifying questions, these are basically sort of class slides, so let's try to make this as interactive as possible. So I'm going to start out by talking about why you should care about data flow, because I think that's not something that's obvious. Why is this an interesting problem that we should be putting our mental energy into? And then I'm going to tell you, sort of pedagogically, from first principles, build up the data flow ideas from a 1D convolution. A 1D convolution is obviously going to be a pedagogical example, but it'll give us the vocabulary that we need to talk about the much more complicated full convolutional layer. And then I'm going to tell you the details of MAESTRO, which is the analytic model and analytic approach for the architectural exploration. So it's going to be significantly faster than even the simulation that we do in MAERI, because it's just going to be an analytical approach. And then we'll go into the hands-on lab, and of course we'll be walking around and helping you guys do the hands-on part. So I think that Tushar covered this very nicely. Why is data movement so important? And it's just because the relative costs are just, very insane. That basically you were talking about somewhere between 100 and 200x to fetch operands from DRAM, as opposed to doing the base multiplication that we have to do these convolutional layers. And of course, if you can put them in a closer SRAM, or an even closer small register file, then you're going to be able to reduce that power a lot. But here's the good news. Look at how the operations break down here. We have, is this a laser pointer? Yeah. We have significantly more multiplies than we have data, right? So that means that we must be reusing the same data in those multiplies, right? That must be what's going on, is that each piece of data must be being reused several times. And so that's an opportunity. So if you have your 7-dimensional convolutional network layer, as we'll talk about, sorry, I don't need the timed animation. So if you have your 7-dimensional network layer that we'll talk about, and you have to map it onto some kind of 2-dimensional hardware array, you're going to take the reuse that is present in the algorithm, in this huge computation space that we'll talk about, and you're going to turn that into hardware reuse, which means staging it into intermediate staging buffers of sort of decreasing size, from DRAM to some kind of shared L2 buffer to some kind of private register file to the actual multiplier. And note that when we're talking about these specialized DNN accelerators for inference, these are not going to be cache hierarchies, right? I think that's an important point that sometimes gets lost in the literature. Everybody from TPU to DLA to all of these different competing inference accelerators, they're all building custom buffer hierarchies, custom buffer structures that aren't going to be using tags, and they're not going to be using dynamic inference to figure out what's going on. Because if you think about it, a cache hierarchy is going to be trying to figure out from the access patterns that it sees what it wants you to do next, and sort of making a dynamic guess at what the best thing to do is. Here we have such a good knowledge of what the workload is that we can save that energy and reduce the simplicity, like use a much simpler buffer structure here, and actually schedule the data transfers in such a way that we still get really, actually probably better hit rates, as it were, than what a cache would end up having. So without paying that dynamic power. But the crazy thing about this is that this is such a high-dimensional problem that there's millions or billions of non-trivial mappings. And the efficiency of any given mapping is dependent on the concrete dimension sizes. And that means two sets of dimensions. The dimension sizes of the problem, dimension sizes of the problem, and the dimension sizes of the PE array that you're mapping on, and the buffer sizes of that PE array. So you have to take into account both as we talk about this. So let's start learning about data flows. So as I said, let's dive into a pedagogical example, which is just to do a 1D convolution, right? So you've got some number of weights, some number of inputs, and that's going to produce some number of outputs. And we're going to do like what I think MATLAB calls a valid style convolution, which means that it's going to sort of shrink the outputs a little. Actually, in neural networks, they don't usually do that. They usually sort of pad the input with some number, and then they end up with the same number of outputs as they would have inputs. But I think pedagogically, it's easier to think that this thing convolved with this will result in a slightly smaller thing over here. So we're going to start by putting this, overlaying this weight over this set of inputs and producing that output, right? So we're going to take this weight by this input, this weight by this input, this weight by this input, produce that output fully. And then we're going to slide the window over to the next set of inputs, same weights, and we're going to produce this, this, and this for that output. So if you wrote that sequence that we just did as code, it would be an array for your inputs, an array for your filters. By the way, I know that these dimensions that I'm using here are a little bit funny. That's because these dimensions are coming from the 6D space, which I've cut out all the extra dimensions. And so you would think, oh, I want to call my weight dimension W and my input dimension I or something. I don't do that because it's actually the 6D variables that I'm using here. And so that's why it looks really funny that the weights is X, S and the inputs is X. And hopefully you guys will understand that by the end of the talk. So, okay, basically we've got our flat arrays. And now we're just going to say for X equals 0 to X prime, for S equals 0 to S, do the very simple convolution of output of X, input of X plus S, and W of S, right? So how often, if we had a data path, a single data path, let's just imagine a system with a single data path in it, how often does the weight and input change, right? With this particular mapping. Well, it's going to change every cycle. Every cycle I'm going to go from this and this to that and that to that and that and that and that, so on and so forth. But what about the output? What about the output? The output does not change every cycle, right? I did 3 things here, and then I moved on to the next one. I did 3 things on that, moved on to the next one. It's supposed to be S cycles. You got the wrong dimension. And so that means that this data flow is what the literature calls output stationary. You will see this term a lot in the literature if you start doing a literature survey. And I think it's very important to explain what do we mean by stationary, because I don't think the literature actually does a very good job of explaining this. So stationary does not mean it never changes, despite the implication of it. It's the data type and dimension that changes the most slowly, right? So let's just imagine we had some toy data flow that needed it took 10 cycles to do a full tile, and it needs 1 sum and 3 inputs to do a tile, but it only needs 9 weights every 4 tiles, right? So then we're going to start out by loading weights and inputs and sums. Then the next time we're going to just do sums and inputs, sums and inputs, sums and inputs, and then weights, inputs, and sums, right, for that particular data flow. So that means that I kind of think of this as like a waveform with an amplitude and a period. The period is 10, and the amplitude is 1 or 3. That's a very imprecise analogy, but it kind of works because you kind of get this sort of constructive interference of waveforms where you get like a burst of bandwidth requirements because I needed to do this and this at the same time. So when we say stationary, we're talking about the data type that changes the slowest, that has the longest period in that analogy. So the locally held tile is usually changing most slowly. And I think that this is very implicit in most of the literature, that usually corresponds to the biggest tile. Because the intuition is if you're going to load a big tile, you're going to want to keep that tile local for a long time to get the biggest benefit out of having that big tile. But that's often a very unstated implicit assumption. The other point is it also often corresponds to the data type that we are sort of done with. And what I mean by done with is that you don't reload it, right? So if you were doing an output stationary data flow, you say, I'm going to do everything for this output. Now everything for this output. Now notice I'm using the same weights over and over again. I'm using the same inputs over and over again, but I'm never reusing that same weight. And so it often, not necessarily, but often corresponds to the data type that is sort of being killed. Maybe that's too violent. It's being finished off quickest by the data flow without any further reload. Later, we're going to see how intermediate staging buffers can leverage the stationarity of the data flow to reduce both the bandwidth requirements and the energy. I think another thing as you start reading the literature to keep in mind is that this name stationary, output stationary, input stationary, row stationary, it's a name that's meant to give an intuition so that you can have a conversation about the data flow. It's not a precise and complete specification of all the behaviors of the data flow. So if I told you that NVIDIA's DLA accelerator uses a weight stationary data flow, that would not be enough information to let you know, is it the same as, say, Gaudi and Now's weight stationary data flow? In fact, they're not, for reasons that we'll try to see as we go through it. Okay, so how do we go from sort of like this sort of C++ loop nest to a data flow, right? Well, we look at this thing not from a C++ perspective, but from the original algorithms perspective. And we noticed that there's not actually a constraint on the loop permutation, right? There's not a loop carry dependence here. However, if you were a C++ compiler, you would think there was, because, and it's very important to notice this, we don't care about sort of where the precision or the saturation issues actually occur, for the most part. In other words, C++ compiler would say, I can't move, let's say I'm using 8-bit data types, I can't move these loops around because I would cause the saturation to happen at different times. Here, as architects, we know that it's going to be harmless because we're going to size the data types in such a way that this never happens. For instance, NVIDIA's DLA accelerator, it uses 16-bit math into a 48-bit accumulator. And some very smart people have figured out that for the network sizes that we care about, 48 bits is enough to never overflow or never saturate, right? So we know now that we have a freedom here to reorder these loops. So we can say, okay, here's a different data flow. I'm going to take this weight. I'm going to put it against this input. Produce part of that output, not the whole thing, just part of it. Go to the next input, keeping the weight the same. Produce part of that output. Go across every input, and so on and so forth, until I've taken care of that weight completely. I'm never going to use that weight again, so now I go on to this next weight. Right? And put it against this input. And now I do it again. I'm closer on making this sum complete, but I'm not done with it yet. And finally, I do the last weight, and now I've changed the dotted box to a solid box to represent, oh, hey, now I have a full sum. Yep, question?
How would saturation be different for this particular?
Oh, no, that probably wouldn't. But I'm just saying it is something that would stop a C++ compiler for...
This is totally
Yeah, exactly. Yeah, this probably wouldn't. But as you had the full 60 problem, there are things that definitely would. Yeah, great question. Right, so now you've completely done your output. Okay, so what data flow is this? Anyone been paying attention to figure it out? Yeah, weight stationary, good. Right? There's one more data flow. Input feature stationary. Some people prefer the term feature, some people prefer the term input, some people prefer the term activation. Right? So how could we implement input stationary? We don't have an index on input. Well, we can just change the loop to use the input as the index, the full x. And now we have to use the inner loop to sort of have this funny math, right? And you have to be very careful with this funny math because, oh, sorry, again, I didn't change R and S. This is supposed to be S here. That this thing has to actually be checked, right? So if I was really going to write it out, it would be if x minus s is greater than 0 or greater than or equal to 0, then I would do it. But I think that would, sort of make the code ugly. But you can imagine, don't fall off the end of the array, right? And that's how you would do input stationary. You would load every input exactly once and send that input to every output that matters, and then go on. Oh, sorry, going the wrong direction. Yep, so that's input stationary. I don't think that input stationary is as interesting a data flow for dense arithmetic, but if you start looking at the sparse literature, most of the sparse accelerators are input stationary. So it's important to understand it from that point of view. Okay, so now let's think, we have a very simple model for just mapping data flows on hardware. This is sort of like my first data flow, right? Let's just imagine there's a single multiplier in the entire system, and we just want to use that single multiplier sequentially to compute all the partial sums for everything, right? So, And we're just going to use a register of size 1. So we've got our backing store, and we've got a register of size 1 that we can use for inputs, partial sums, and local buffers. So just one register for each. So if you look at the algorithm, what's the algorithmic minimum accesses number to backing store if you had like infinite buffering here that you didn't care about? Well, you would have to load every weight once, every input once, and every partial sum once. So that's like the absolute lower bound. You will never beat that. Right? It's like the oracle in this state. And the other side, what's like the adversary? The adversary is something that loads everything from backing store all the time. Now, it's never going to like spuriously load something. It's not going to be like, oh, I'm going to load this 100 million times. It's just going to load them, you know, enough to do the math and not any spurious loads. That would mean that you would have to take every weight by every output, every input by every weight. And so these are the sort of goalposts. The best you can do and the worst you should do. If you're doing worse than this, something is really wrong. Okay, so now let's look at how the data flows react to the buffers. So the first question we're going to ask is, how big of a buffer size would we need to never refresh anything, right? So let's look at our data flows: weight stationary, input stationary, output stationary, right? And you'll notice that there's this weird diagonal that's going on here, right? And that's basically not a coincidence, I don't think, right? So here, if we do a weight stationary data flow, we only needed a buffer of size 1 for the weights, and that was absolutely enough to cover all the weights we were ever going to load, because we loaded a weight, did it for every output, and every input, every output, and then we moved on to the next weight. So we only needed a size 1 weight. But we needed a big buffer for inputs and outputs in the 1D case. And input stationary is sort of, we move where the 1 is. Now we only need a buffer of size 1 for the input, but now we need to be able to hold S weights and S outputs. And output stationary, the same thing. We moved the 1 over here, we're only going to hold that, and we only need a buffer of size S for inputs and outputs. Okay? How many times do you access the buffer? Well, notice that these buffers of size 1 get accessed a heck of a lot of times, right? Which is good. Buffer of size 1 is cheap, right? So that's desirable property. And also notice that if you multiply what's going on over here by what's going on over here, you always get Sx prime. That's not a coincidence. Sx prime times 1, S times x prime, S times x prime times S. See that? That's not a coincidence either. Okay. So far we've been saying, what buffer size would we need to actually, have a zero size, no buffer, no refetches? This is saying sort of how big of a buffer, how many times do I access the buffer, right? And I don't think this is as important. Let me go on to the next slide. I think it explains it better. So here we've got the same table, and now there's going to be a major energy implication, right? This is in some sense one of the most important slides that we're talking about, right? So we've got 1, we've got Sx times of 1, x, s times of x. This is the total sort of accesses. That everything here is going to be Sx prime, as I said. Now let's imagine that we had some magical function called f, which is just always gives you the energy cost of accessing a RAM structure of size x. So f of 1 tells you how much energy it costs to access a buffer of size 1. F of 100 tells you the energy to access a RAM of size 100. Okay? Now, the weight stationary data flow is going to be f of 1 plus f of x prime plus 2 times because you're doing a read and a write of the output of x prime, right? So I'm going to label that red because it's taking the 2 and it's applying it to a very expensive structure. If we did input stationary, f of s plus f of 1 plus 2 times f of s. And so output stationary for the very simple 1D case, this is actually not going to be true when we go to multiple dimensions. But for the very simple 1D case, we like output stationary because it takes that 2 to x factor and puts it on the cheapest thing, right? 2 times f of 1 plus f of s plus f of this. It's strictly cheaper than this. So the takeaway here is that there's a significant difference in buffer access energy cost based on the data flow. Okay? But here I've been asking the question, well, what if I paid for a big buffer, a buffer that was arbitrarily sized to hold all the weights? What in reality, you have some fixed buffer size that you fixed at design time, and that buffer size is probably not going to be big enough to hold all the inputs or hold all the outputs. So let's sort of make things more realistic and start talking about that. So yeah, getting more realistic. So first, let's add a level of buffering. So instead of sort of just flat buffers in the backing store, we're going to have some buffer that's not of size 1 anymore for each data type. So what does that start looking like? Well, it makes the loop nest a little bit more complicated, because what you do is you factor your x prime and s into x prime 1 and x prime 0. I know these are not the best names. It would be better if I had subscripts and stuff like that. I was using pretty math mode. But so here, remember that x0 and x1 multiplied the original x, s0 and s1 multiplied the original s. I don't want to deal with like edge conditions for this tutorial, because edge conditions are a little bit too of an implementation detail that, by definition, they don't have a ton of impact on the. So let's just assume that this is a proper factorization. Okay, it'll make our heads hurt a lot less. Okay, so then what we do, we have the exact same original computation, but what we've done is we've redefined these variables x and s in terms of the index here, right? So x1 times the tile size plus your offset into the current tile, right? Read this as, yeah, exactly. This is what tile am I working on? This is where am I in that current tile? Any questions about this? Okay. So now, how does the mapping sort of affect the energy cost? We already said that the energy it takes to access the buffer is a function of this buffer size. But notice what's actually changing and what's not, right? So our innermost iteration here is on S0, which means that these things here are not changing, and these guys are. And then you go up here and you change it, and these things change a little bit for the next sort of set of loops. Yep. Okay, I think we've said all of this. Okay, yeah. Here's a good point. So far we've just been talking about the number of accesses to a buffer. But of course there's actually 3 components. If you have a buffer of, at level L, then you have to talk about writes into that buffer from level L plus 1, which we're going to call fills, and then data that needs to be transferred from level L to a closer to the data path, that's a read, and then data that's returned for partial sums. In a convolutional neural network, the only thing you need to write back is the partial sums. The weights and the inputs are read-only data. So data for the partial sums, you have to worry about data that's coming back from level L minus 1.
Just wanted to make sure the pen drive is being passed around.
Yep.
So please install the VM.
Yeah, is there anybody who wants the pen drive that hasn't gotten it yet? Raise your hand. Yeah. So who has a pen drive that they can pass over? Yeah. Good point.
And the same thing for the sign-up sheet, but that's not a time constraint thing with the pen drive, so that once we get to the demo parts, at least
Right.
you can start running.
It takes at least a minute to transfer the VM files, so maybe 2 minutes. So, okay. All right, so let's dive back into how we figure out what these access counts are actually going to be when we've added a new level of buffering. So we have our level 1 tile and we have our level 0 tile. And we're going to say, okay, at the beginning of time, I'm going to be working on this S10 tile, S1's first tile. Right? So I'm going to load the first tile of weights. And then when I increment S1, I move to the next tile. If I increment S1 again, I move to a new tile. And again, remember this, S0 was our offset into that tile. And that changes every time, oh, sorry, I didn't change the variable name again. That's X1. X1 changes. So here we are. Yep. So for this particular data flow, this is what you would call, let's see, level 1 iteration. Yep, this is how many times you read it. I think you guys can look at this offline. I don't think the math is so interesting. But basically, it's very similar to the math we were seeing before, but now you'll be using the level 0 and the level 1 to figure out the transfers between level 1 and level 0. But the point is that this is a disjoint, or what we could call partitioned, pattern of reuse. That this tile and this tile and this tile are distinct pieces of data that do not overlap. Now let's look at the input data type for the same data flow. This is not changing the data flow, it's just looking at the other data flow, data types for that data flow. The input, we have this tile for one S1 equals 0. And when we access it, we were accessing it plus our offset into the weights, right? So this base index calculation remained the same, and this one changed, right? So there's an overlap here. And then there's going to be an overlap again. And this is what we refer to as sliding window. And this is the thing that you'll see a lot in the literature. You're not going to be reloading this entire tile. Instead, what you're going to be doing in your buffer is you're going to be chopping off this part of the buffer, filling in these new things into the thing you just chopped off, and using a circular buffer strategy so that you rebase what 0 means. Yeah. Right. And this is saying that the outer loop is going to sort of have a funny effect where you're probably going to have to go back and reuse these same inputs. Yeah, and there's a halo. Yeah, that's what it's saying. There's a halo here. Okay, and you could go through this math again offline. I don't think you need to worry about it. But the point is that you can algorithmically derive what the total number of reads and transfers are going to be. And this is the sliding window reuse pattern. If we look at the output, that's determined by this index right here, right? What output we're working on. And that's just going to be the same thing, right? Because it only changes when this x0 changes. So over the entire S0 iterations, we're going to be just doing the same thing, and then we're going to repeat and do the same thing again, right? The S variables have no impact on what O you're working on. So even though big S1 changes, you have to go back and reuse these same partial outputs, and then do it again. So that means that for this particular data flow, these partial sums would need to be written back to a global buffer and reloaded when the next big S1, the next S1 tile got loaded. And you can do the math on that too. Basically, the cost here is that instead of you being just SX or SX prime like it was before, now it's going to be something for L0 and something for the number of transfers from L1 to L0. Yeah, but it's all derivable statically based on the number of PEs, the shape of the data, and the mapping strategy that you've chosen. So far, we've just been thinking about the fact, okay, what if there's one PE in the entire world? Right? Of course, that's not going to be true. We're going to want to actually exploit parallelism, like Tushar said. So let's just pedagogically imagine that there's another new dimension of PEs, and they're going to be just sharing the same buffers, right? Just two multipliers sharing the same buffer. So how would that be reflected in the loop nest that we've been talking about? Basically, it's just going to be a new level of loop, but it's going to be like a parallel level of loop. You could think of it as like a parallel for, because you're going to be doing that level at the same time. And of course, we can imagine having sort of private L0s or shared L0s. This is a choice for the architect to make, whether you want to have several sort of multipliers or data paths sharing a set of buffering, or you want to have private buffers. Very similar trade-off to what you see with cache hierarchies. All right, so now here I've put the parallel fors. So I haven't changed the data flow. It's still x1, s1, x0, s0 in the same order. So it's the same data flow. But instead of temporally doing these outer levels, we want to do them in space instead of in time. right? We want to do them in parallel. Yeah. And so we could say, okay, I've got two PEs, so that means the concrete value of big X1 is 2. And here, this is going to be, S1. This guy will do, one PE will do the S1 equals 1, one PE will do the S1 equals 0. And so we could just take it out. Right. So now I've just not using the S1 variable. Well, yeah, so for one PE, you will set this variable here to 1, and for one PE, you will set the variable there to 0, which means that you will be working on a different set of stuff. So yeah, so one guy will be working on this set, one guy will be working on that set, because this S1 variable will project them into a different space in the dimension. And so in parallel now, we'll do that, and produce two outputs at the same time. And then slide, yeah, and do it again. So why is this very important for our data flow? It's very important because look at what's happening. At the beginning of time, I'm going to use this sort of C++ stream notation to mean transfer. So at the beginning of time, this guy is we're going to transfer weight 0 to this PE. And we're going to transfer weight 0 to this PE. Right? So they're both going to be getting the same thing. So is there an implementation opportunity there? Right? Absolutely. You can do a single fetch and multicast the data. Right? So you can do a single access into your big expensive buffer, your shared buffer, and then you can multicast the data to two guys, rather than doing two accesses to your big expensive buffer. Yep, question?
Is there an energy model that says that the cost of accessing one item of data plus doing multicast is lower than just two separate?
Yeah, right. That's a good question. We're not going to be talking about specific energy models today, but in general, because there's not just going to be two PEs, there's going to be 64 or 256. It absolutely is. So it's a pretty easy trade-off to make. But you're right. In practice, it's not going to be divided by n. It's going to be divided by n plus some constant to do the actual transfer. Right. But yeah. And it also does mean that you need an on-chip network that has the capability to do multicasts. Right. So if you don't have the capability to multicast, then you would have to do temporal accesses. But that would cost you both bandwidth and energy and time. So I think it's probably worth it to put the multicast capability in. That's also a big distinction between, even a GPU, even with the tensor cores, they're not multicasting data across SMs in the GPU. If two SMs are loading the same data, you're doing two accesses to the L2 cache. But of course, within the tensor core is doing the spatial reuse of the data in the GPU. But this isn't a lecture about GPU. This is a lecture about ASICs. If you guys want to hear about GPUs, talk to me afterwards. Okay, so now we've got our 1D convolution with spatial. How do we recognize multicast opportunities just by looking at this? Well, notice what's going on. We had this parallel level, which was dividing things up into things that we wanted to happen at the same time. And now look, this was based on x1 variable. That x1 variable does not show up in the index, right? The index is independent of that. That means they must be doing the same thing. So that's how you recognize a multicast opportunity, just by looking at the data flow that you've chosen. And you can work it through that, you can also, you can't multicast the inputs because this guy's doing, well, maybe it may or may not be the same input. Yeah, right. And you can go through all the things. Again, I won't do this online. You guys can download the slides and do it yourself and work out what are the things that you can multicast, what are the things you can't multicast.
And I'll add a small point on it.
Yeah.
So in terms of the multicast, you could also implement the multicast as a store and forward. In the sense, you could just read the weight into one of the PEs and keep forwarding it, which is kind of what a systolic array, the GPU study does. So in some sense, it is still a multicast. Of course, the energy cost would be different. I mean, but there you're passing it through just latches rather than doing those reads.
And that's coming from a real network on chip expert. So if he says it, then we'll believe it. Yep. Okay. Right. So, okay. What about the weights? So this is saying, are there other ways you could have done the spatial partitioning? There we were spatial partitioning the inputs. What if we had a giant number of weights because we were working on several different input channels in a real data flow for a real convolutional layer, and we wanted to partition the weights instead? How do we do that? Well, we just go back to our original data flow, and we now say, okay, for the first PE, I'm going to set this x1 to 0, and set for the other PE, I'm going to set it to 1. And down here, I'm going to set this to the number of PEs. So I've gotten rid of the opposite loop that I got rid of before. And so this is what it ends up looking like. Nothing too surprising. How does that end up working? Well, look at what happened here. I said for one PE, I was going to set this x1 variable to 0 statically, and for one PE, I was going to set the x1 variable to 1. But that means that you can actually end up with the same index, right? Especially for things, early things. So how would you handle that two different PEs are working on the same sum? That's what we call a spatial reduction, right? And no other multicast opportunities came off. In fact, instead of a one-to-many, which was a multicast, in some sense, having the same index occur here for multiple PEs is a many-to-one, right? So it's a spatial summation. So you can imagine that as having a additional plus guy that's doing the sum between these two guys. Or you could just imagine that the PEs are doing it, that this guy does his thing, passes it to him, and this guy adds it up. I've seen architectures do both. MAERI is more of the first style,
yes.
Right? So when we do the second tutorial for MAERI, it's going to be doing the style where the addition is outside of the PEs. If you see IRIS or SCNN, they're definitely doing the style where the plus is happening inside the PEs. What if you're doing a data flow that can't do a spatial sum? Your hardware doesn't have the capability to do summations across different PEs. Well, then what you've done is you've got an illegal mapping. You've got for any given hardware, based on the implementation characteristics of the on-chip network and the sizes of the buffering and whether it can do these spatial sum characteristics, there are data flows that simply will not map onto that architecture. So the mapping tool has to be architecture dependent, and it has to be able to say, this is the best mapping I found for this architecture. So as architects, our job is to sort of figure out what the sizes and shapes that our users will care about and provide good mappings for all of them, right? Okay, so that is all in the 1D space. So now let's try to make things even more realistic. So the first thing is, and I told you that I'd explain where these variable names came from, is we're going to make it 2D, right? So we're going to have R and S and Y, and yeah, this is Y prime, because it's just a function of Y and S. Then when we have convolution neural networks, we're going to add several input channels. So that's usually called C in the literature. So C is number of input channels. And of course, what you do in a neural network, I think most of you guys know this, but just to page in our caches and our mental caches, is you're going to do a summation across these input channels, right? So this is like a dot product. Now, on top of that, the reason that this gets more and more complicated is that we're now going to add output channels. So we're going to have a different output channel, two output channels. Each output channel is going to have a distinct set of weights. So the total number of weights is C times K times R times S. Oh, batteries died on the weights. Sorry, Jim. Yeah. So, right. Yep, so that's why this is such a complicated problem. So everything that we've been doing has been 1D so that we don't break our heads. But actually, a lot of the strategies that work best for 1D don't work best when you go up to this CNN. So output stationary is by far the best for 1D, but actually most of the real networks are some kind of weight stationary because there's so many weights here, especially on the later layers. And most of the modern networks are getting to have even more and more weights. So if we wrote this out, even before we started tiling it for multiple levels. This is why you already have 6-layer loops, 6 for loops for K, C, Y, X, R, S. And this is the full convolution problem that you're actually doing. You often see people talk about batch size. Batch size means that you actually have several images available to do with the same set of weights. That may or may not be available depending on the deployment context. If you are an inference engine that's coming from a camera and the camera only gives you one image, then you can't do batch size. If you're doing training, the batch size is almost always available, as far as I know, because nobody does non-batched gradient descent. So if you add batch size, that would be another level, 7th level, and that would completely change the amount of data flows that are available because you can then reuse the same weights on different images. So whether or not batch size is available is a very important consideration. So this is an utterly gigantic space of potential tilings, right? We saw several different strategies just when we had just 1D convolution. So how do you explore that, right? So one option would be that you could do cycle accurate modeling. You know, you take to a cycle accurate model of your architecture, and here's your realistic data size for VGGNet, but that's way too slow. It's way too slow for given this space. And so the solution that we're proposing is to use an analytic model, and the analytic model is specialized for the CNN problem for efficiency reasons. And that's what Maestro is. So yeah, basically it's an analytic model, as Tushar said, where you take, I'll try to use the mouse instead of the laser pointer, take some description of the neural network, take some description of the accelerator architecture, take some description of the data flow, which maps those 6 levels onto it, and then gives you the number of access counts to L1, L2, the knock requirements for the maximum bandwidth, and the sort of roofline throughput of the best, even if you had maximum bandwidth, the best that this data flow could do. It's not going to execute or simulate anything. It's all going to be deriving these things from these inputs. So it's mathematical equations. So the way I would think about this is that it's a first cut estimate that later allows you to focus in where you want to do your deep dive cycle accurate simulation. You say, oh, I think this is the interesting part of the space. I'm going to now zoom in on this space and do cycle accurate simulation within this space. And we're still validating the model. Once we have the validation completed, we'll release this as an open source tool. For now, we've given you guys the binder. Yeah, one question.
What does the model predict? Resource cost?
Access counts. It's not an energy model. It says I had to transfer n things into the L1 buffer at this. So let's say I'll show you some more concrete examples as I go. So if I don't answer the question, but it's going to be something like every 400 cycles I needed 20 weights, and every 400 cycles I needed 30 inputs, which gives you the network bandwidth requirements and so on and so forth. Yeah, so how does it describe the architecture? Well, the architecture is just going to be a spatial array of PEs. It's very, very general. It's not anything fancy. They're going to have an L1 buffer and a shared L2 buffer connected via a non-chip network. So you could kind of think of that as like an iris-like architecture. And then the input parameters, you can set the number of PEs, you can set the vector width of each PE, cap the on-chip network bandwidth, set the average number of hops, does the on-chip network support multicast. And the layer is just going to be what's the C and K dimensions, what's the RNS dimensions, and what's the X and Y dimensions. You guys don't need to learn the details of this for this particular tutorial, but I did just want to cover. These are the ways that we describe the data flow. You can do a temporal map of a particular variable. So the variables are K, C, X, Y, R, S. And that would say, at the beginning of time, do the first tile. At the next step of time, do the second tile. You could also do a spatial map. That's like that parallel 4 that we were talking about. It says, I want to take the first tile, give it to the first guy, take the second tile, give it to the second guy. The other thing we have is what's called tile. This is maybe not the best name, but it's what it is it says, make these PEs into a group. Right, so make these PEs into a group, and that's how we just describe various existing architectures. Yep.
Yeah, so you can compose the PEs into any dimensions using this kind of description. So yeah,
right.
Generally.
Basically, that's how you get 2D PE grids and stuff like that. You can also do these merge and unroll. I don't think that's as important for this, but you might see them as you look through the files.
Just to add to June's point, so the 2D PE grids is again, you probably see a lot of architectures which do some sort of clustering of like multiple PEs together into a cluster. So that's kind of the pragma that's describing that feature.
Right. Exactly. So basically, using Maestro, we've described a bunch of existing data flows, and you can look through the details. But basically, it's going to be a temporal map of K, a temporal map of C, a temporal map of this, and then a spatial map of something else, with maybe some unrolling thrown in there or tiling. Don't understand this slide. I don't want you to understand this slide. Just ignore it. It just gives you some intuition as to how it's calculating what the math is behind it. Basically, it's going to calculating the L1 reads and L1 reads for each data type and writes for each data type. So here I've just got a small example of what the kind of output you would actually end up getting. I hope this answers your question. Basically, and by the way, this is not a comparison of existing like DLA as an architecture. This is the data flow that DLA uses on this abstract architecture. So it's sort of saying what would be the best data flow for this architecture. It's not saying anything about the actual performance of any given actual system, like Shebeam now. But basically what it's going to give you is going to say, okay, this is the number of max I end up doing, this is how many times I had to do the L2, L1 read weight, L1 read input, L2 read weight. And then you could then pass these numbers to your energy model and get the appropriate scaling for what the size of the buffer is. Okay, so I'm going to switch to a demo. Let's see. So is it up already? It's
You should just go to VirtualBox.
yeah, VirtualBox. Yeah, great. Yeah.
Yeah.
Yeah. Okay. Great. Okay, so you should be able to log onto the virtual machine if you have one of the people who have taken the pen drive.
So again, yeah, people who need pen drives or these pass them around.
And the pen drive has VirtualBox on there, so if you need to install VirtualBox, you can do that. This is basically what it looks like. So there's only one login user, and the password's right over there. Lowercase MAERI 2018.
Yes.
Oh, here's a question. I have one question.
Yeah, question.
So I understand the lecture has been focusing on the convolutional layers.
Yes.
But for like fully connected layers, which are common for the audio and speech models, is the tool also capable of handling those?
Not yet. So what we see maybe this is the bias of NVIDIA. NVIDIA, being a graphics company, tends to focus on computer vision neural networks. So that's what we think of most of the time. In the graphics neural networks, there are fully connected layers, but what's weird is that those fully connected layers are often expressed as convolutional layers. So you have a 11 by 11 with 500 channels. You just say that that's the number of neurons in a convolutional layer, right? And so we can actually express our fully connected layers as convolutional layers. The other thing is that I didn't mention is that it also doesn't include like the activation functions or the pooling layers, and that's just because 99% of the computation in these networks is in the convolutional layers. But that's a good question. I think we want to support fully connected layers and other things like pooling layers as just future work. Yeah. And especially when LSTMs and recurrent neural networks. I think that's a good point. So I think that's probably just my bias. Sorry. Okay, so you should be able to sort of reproduce what I'm doing, which is basically that you should be able to get a terminal, get logged in, see this kind of thing. There's a directory called ISCA 2018. That's where everything for this tutorial is in. There's two directories for MAERI and Maestro. Let's go into the Maestro directory for now. Oh. Okay, so we basically have pre-baked for you guys some set of data flows and layers. Let's look at the layer descriptions first. We basically have early layers from VGGNet and later layers for VGGNet. Actually, I think one of the things we didn't say throughout this tutorial is that the early layers and the later layers have very different characteristics. This is one of the reasons that data flow matters. Early layers tend to have very large width and height and a very small number of channels. All right, so let me just open up a description and we'll see that. So VGG-conv2, 64 by 64, but with 64 channels, but 224 X and Y, right? So not too many channels, but a very large X and Y. If I look at VGG11, now you see that these variables have sort of flipped. 512 by 512 with very small X and Y, right? So that's why this data flow stuff starts to matter. If you had a data flow that was very good on late layers, it probably doesn't work so well on early layers, and vice versa. But notice that the total amount of data is actually kind of funnily almost the same. Not exactly the same. In fact, it's a little bit bigger on the later layers. But you know, the first order of thumb, even though the heuristic in your mind should be that even though I've completely changed the shape of the data, I haven't really changed the amount of the data. Then we also give you several layer descriptions. So, sorry, not layer descriptions, data flow descriptions. So basically everything that we had in that table, a DLA-like data flow, a balanced data flow that just does a little bit of everything, a weight stationary data flow, a row stationary, which is the iris data flow, and you can take a look at them. Let's look at the row stationary one. Right, so again, it's just temporal map, which is T-map, spatial map, which is S-map, and for each one it picks a size and an offset, and then what variable it applies to. If you see a different offset than size, like what's a good one that has that?
It's the sliding window.
Yeah, but where can I show it?
Is there an example to show that somewhere?
Yeah, there should be.
Which one? The
Let me double check.
weight stationary? No. Balanced maybe?
Yeah, balance should have.
Yeah, right. Right. Yeah, exactly. So here when you see this kind of thing where the offset is smaller than the tile size, that's how this tool represents the sliding window. That it's got, you know, a tile size 3, but then the offset's 1 in there, and 3 would be jump to the entirely next tile. Okay, then to run the tool, what you have to do is provide, I'll just go back to the PowerPoint. Oh, sorry. You have to provide it a layer name, a data flow name, a vector width, a max bandwidth, oops, I forgot to erase. Does it support multicast, 1 or 0, average number of hops, and the number of peaks.
Right, so if you just type just excuse the binary without argument, then it will show which argument you need.
Yep. Great. All right. No, don't have focus. All right, so let's do an example like MAESTRO of, get the help, MAESTRO of VGG2 and data flow of DLA, and then let's say that we have a vector width of 1, a knock bandwidth of 8, does support multicast, average number of hops is 2, and number of PEs is 16. Okay, and now of course it just dumps a bunch of output at us, which we'd like to redirect into a file. Let's say 16.txt. All right, so if I open up 16.txt, then first of all, it's just going to print things like what data flow it ended up using, and you can just see that. And then here's the counts. Right, so for this particular thing, it said, this is the number of times that I read the L1 buffer regardless of data types. This is the number of times that I wrote the L1 buffer regardless of data types. This is the number of times that I read a weight. This is the number of times I wrote a weight. And then here, this is the reuse factor. So that's the reads divided by the writes. So this particular data flow reused the weights 16 times. And then the inputs for this one and the sums. Right, so here we can see that this was probably an output stationary type of data flow because the sums were 1 to 1. Oh no, sorry, that means it's not output stationary. Yeah, and the same thing for the L2. And then it gives you the analysis of L1 to L2 knock bandwidth, 16 elements every 256 cycles. So that's how many sums it was writing back, right, June? Or did we get the payouts?
L1 to L2.
Yeah, L1 to L2 is how many sums it was writing back, 16 elements every 256 cycles. So this particular thing took 256 cycles to produce 16 elements, and from L2 to L1, it needed 512 elements to do that. So it needed 2 elements per cycle. So hopefully there was some multicast. And then the roof line is that with 1 gigahertz talk, and the total number, full cycle estimate, basically. So with that, we wanted you guys to try this hands-on lab, which we will walk. But essentially, we have a simple exercise. The first exercise is to pick a data flow in a layer, such as conv2 and DLA, but you pick, and then just keep on doubling the number of PEs. So do 1, 2, 4, 8, whatever up to. And at what point do you start to see diminishing returns? And you can think about why is that, and is there a way to fix that? The second exercise is just, okay, what happens if you start changing the numeric parameters of a given data flow? So if you say, okay, instead of tmap 4, I want to make it 8, or 16. How does that affect the counts? And how does that affect the sort of transfer bandwidth and the number of cycles that it takes to do the tile? And at that point, you should definitely start to see differences between what happens on an early layer and what happens on a late layer. Then the third sort of exercise is to just pick a fixed layer in architecture and just sweep the data flows and see how, for that layer in architecture, what is the best data flow for that particular architecture, according to MAESTRO. And which one has the sort of, pick a data type and say, okay, which one did best for that particular data type, if that's the thing that I think I care about most. And of course, if you're feeling ambitious, there's a challenge to try to design a new data flow, and has the following properties. Can you sort of limit yourself to 16 PEs and bandwidth 4, which would sort of emulate a mesh, and then can you get a really, really low L2 to L1 bandwidth using just one SMAP and 5 TMAPs? Can you do better than all the provided data flows on late layers, even if you're worse on early layers? That's sort of the challenge. Oh, and don't forget we have a coffee break, 10 to 10:30. So I think what we'll do is we will just start working. We'll walk around and help you guys, and then of course we'll do the coffee break. If people want to stay here and work throughout the coffee break, that's great. Otherwise, of course, feel free to take the coffee break. Then June will start the MAERI part of the tutorial at 10:30. Yeah. And of course, if you're not interested in the hands-on part, you can go and take an early one. We won't be insulted. Okay.
So also